Next is user mode memory management. Here what I want to discuss is the different types of allocations inside the user mode address space. What are the different APIs used to create those different types of memories? In the bottom of the stack, we have something called virtual alloc. This is a Windows API. You can check the documentation if you want. Using virtual alloc, we can commit pages. Commit pages are pages which has RAM backup. So it has a valid page table entry. Only committed pages we can touch. When I say touch, I mean instruction like move dword ptr, then the address, and then the register, like the one we have seen. So such kind of instruction will work only on committed pages. Committed. Another thing virtual alloc can do is reserve memory. Reserve memory is not as good as committed. Reserved. Reserved memory is just a range reservation. It is not committed and there is no RAM backup for reserved memory. When a thread is created, most of the stack is reserved. Normally in 32-bit, a 1 MB depends on your linker configuration. A 1 MB reserved memory is allocated for that particular stack, but that is not committed. So there is no RAM backup, RAM or page file backup. So which means that if you touch a reserved page or segment, reserved segment, you will get a page fault and you will get access violation. Reserved memory, we have to commit first. Why do we reserve? We reserve because we want to commit later, we want to use it later, and we need contiguous addresses. Just like the case of stack, we cannot have stack in different places. Stack cannot be segmented or fragmented. So stack has to be a contiguous chunk of 1 MB memory. So that is why we reserve memory for stack. So what reserved segment does? What it does is when we call virtual alloc with the mem_reserve flag, all it does is create something called virtual address descriptor. Slightly out of the context of our discussion, but all we need to understand is that we cannot touch the reserved bytes. We need to commit it before we touch it. Committed bytes we can touch. All the memories we touch, global, heap, stack, everything, .NET heap, Java heap, Golan, JavaScript, everything is committed. When we debug, when we take the dump of a process, it is the committed bytes we are copying. Those are the bytes which really matters to us. Anything outside is just question mark, like the one we have seen, including the reserve. If you do a DC on a reserved byte, you will see just question mark. That is done by the virtual alloc. So virtual alloc normally deals in terms of pages. Normally we don't use virtual alloc for allocating small chunk of memories. Virtual alloc is normally not directly used. Virtual alloc internally calls another API called NT_allocate virtual memory. That is the NTDLL equivalent of virtual alloc, which is also available in kernel mode. Little more familiar person is malloc. Malloc is the CRT heap alloc, which internally calls heap alloc. Heap or NT heap or any heap manager, any user mode memory manager is like a retailer for the virtual alloc wholesaler. So what it does is it allocates bigger chunks of memory, cut it into pieces, do some management like, clubbing when you free two, three different pieces, it'll club the memory together, the segment together, etc. Some of them has garbage collection, so on and so forth. All it does is it does some management and give you pieces of memory, 1 byte or 4 byte, any amount of memory you need, you will get from a typical heap manager. The NT heap manager, where we get our malloc, is no different. So it calls heap alloc internally, heap alloc. It is also a documented API. And heap alloc, not every time, but whenever it is out of the committed space, it will call virtual alloc. Now the thread stack is also having a guard page and stuff like that. When you touch the guard page, it commits that page dynamically. I'm not going to the details of it. So thread stack, we have seen it's a 1 MB contiguous memory in user mode. 1 MB is reserved. 1 MB is reserved. Now another type of committed memory is the binary loaded, the mapped binary. We have seen that. That is where all the code lies in the mapped binary. All the functions, all the function pointers, then the global variable pointers, static variable pointers, all those are inside the loaded binary or the mapped binary. So that is another set of committed bytes. That is also committed bytes. Those are also touchable memory. You can touch, you can read and write using move instructions in the CPU. You will not get an access violation. That is what I wanted to discuss in the memory management of user mode. The other details we have seen, the nature of the address and the address translation and stuff like that. So look at the documentation of these functions if you like. Heap alloc, especially virtual alloc. Virtual alloc will give you a lot of details of how user mode memory is managed. In fact, we have the sample application coming for all these scenarios. So virtual alloc leak, then heap alloc leak, malloc leak, all those samples we will be seeing when we look at those scenarios.